Hello, I'm David. I'm the coordinator of the Maths Learning Centre here at the University of Adelaide. It's semester 1, 2024, and this is the revision seminar for multivariable and complex calculus. Okay. All right. So I've had some requests, things that are related to derivatives and integrals, and I'll do them first and we'll see how we go after that. Sure. Right. Person who asked this may have further comments to add, but I'm going to say some things. Bear with me, just thinking. Well, right. Yeah, I can start talking now. Maybe not. I'm going to start here and I might have to go into other places. If you do an integral across a volume of some function, I'm going to start here. So suppose you have some scalar function. Scalar field probably in this course is what they called it. But suppose you've got some function that takes every point in 3D space and produces a scalar as the answer. And then I'd like to integrate that across a volume in 3D space. So some sort of volume in 3D space, that's V. And at every point in space everywhere, but in particular inside the volume itself, there is a number that you can calculate, which is the value of F. So every point has a number of its own. And what I'm going to do is I'm going to add up the value of that number. You're right? The value of that number, taking into account how much space it spends being close to that number. And that's what this dx, dy, dz here is. That's a little tiny piece of volume, which is dx wide in this direction and dy wide in this direction, dz high in this direction. The little box, and the idea is that if the function value was the same on this entire little box, then when you added up the function value, taking into account the area, then you would go, well, since it's all the same, whatever the number is, times the volume of that box, and then you'd add that all up across the whole thing, and that would be the answer. And as long as your box is small enough, you can assume that your function's constant on the little boxes. Cool. But the thing is that in every location, the function value is a little bit different. And so the only way to be absolutely certain what this number is to locate every point in this volume. So you have to describe how to figure out the location of every point in that volume, one point at a time. Not really one at a time, but close enough. So if you're lucky, your volume's already a box, and then that's great because your 3D space is already arranged in a box-like way with the X, Y, and Z coordinates. But if you're not lucky, then you may have to change your coordinates in a different way, which means parameterizing the space differently. So it may be important there is more than one way to locate every point in space. You can do it with an X, Y, and Z coordinates. You can do it in a couple of polar forms, and there's all sorts of other ways to do it too. And the problem is you're trying to add up how much, like based on each little tiny volume, what the sort of the average function value is in that spot. And if you are locating points in this volume in a different way, the little pieces are a different shape and size. And so you have to take that into account when you make this sum. That's the idea. So if you parameterize space differently, e.g. U, V, and W produces an X, Y, and Z coordinate, then when you do this integral, you'll track the values of U, V, and W to tell you where you are in the volume, and that will correspond to like changes like a du and a dv and a dw will correspond to something times dx, dy, dz. It will just be not quite the same, or possibly dx, dy, dz is something times du, dv, dw. It works the same way the other way. You might like this. Because what you want is you want to track this across the values of u and v and w. And so when you do the integral as an ordinary integral, the way you were taught to do integrals in one variable calculus, you're going to need a du and a dv and a dw here to do that integral. So you're going to have to somehow convert this dy, dx, dz, which is dx, dy, dz, which is this, into a u, du, dv, dw. And the only way to do that is to know how changes in x, y, z or u, v, w are related to changes in the other. I'm going to stop in just a second and check how we're doing. But it's just easiest with an example. So if, for example, you did traditional spherical coordinates, I don't know if traditional is the right word to use, but that's what I call it. Or at least spherical coordinates as they are described in this course, then every point is located by two angles and a radius. So you can pick a radius for a sphere. That is not very spherical, but anyway, close enough. You can pick a radius for a sphere. Really not doing a very good job there at all. And then within that, you can pick an angle down from the top, which is phi traditionally, and that will pick a height on your sphere. And then at that height, you can draw a circle and you can pick an angle around the edge of that circle, and that's theta. And so what it turns out to be, I have to draw this diagram every time, 3 diagrams in order to make sense of the spherical coordinates. So from the front, there's the x-axis and there's the z-axis, and there's this circle here, which is of radius r. And there's this angle phi coming down from the top, in which case the height of this above the x-axis there is cos of phi, because it's next to the angle phi, cos phi. And this distance here is r sine phi. Yeah. And what I can see from this little circle that's being traced around the top of the sphere, that's from the side, it looks like that. And it has radius r sine phi. And then from the top, there's your big sphere there. And we have a circle that's a little further in, like that. And its radius is r sine phi. And then all the points on a circle are always located with radius cos theta, radius sine theta. That's how a circle works. And so the x and y coordinates will be the radius, which is r sine phi, times cos theta, and the radius, which is r sine phi, times sine theta. And so what you end up with is this, that the x and the y and the z coordinates are r sine phi cos theta, r sine phi sine theta, and r cos phi. That is your spherical coordinates, and your r is as big as you need it to be. If you're doing the entire space, the r can go up to anything. But it has to be positive because it's a radius measured from the center outwards. And the phi is measured from the top down. And so phi goes from 0 to pi. And the theta is measured around this circle. So it goes from 0 to 2 pi. Yeah. If you Google spherical coordinates, you may end up with the phi here going from minus pi on 2 to plus pi on 2. Different mathematicians make different choices for this. You just have to pick something that produces all the answers for cos. But if, oh crap, anyway, that's, if theta is going from minus pi on 2 to plus pi on 2, this is sine here and this is cos here. So it'll, yeah, just be careful if you Google it. If it's not from your textbook, it might be a bit different. So this is our version of traditional spherical coordinates. And what it tells us is that based on an r and a phi and a theta, we can locate an x and a y and a z. And if we move the r, then the x and the y and the z will all change. And if we move the phi, then the x, y, and the z will all change. And if we move the theta, then the x and the y will change, but the z will stay the same, because it doesn't have theta in the z there. And so we have to keep track of when you move the r, the phi, and the theta, because we would like this, we would like to keep track of where we are based on the r and the sine and the theta. That's what these integral signs are going to do. We're going to need a dr d sine d theta here. So we're going to have to figure out how dr d sine d theta is related to dx dy dz. And it turns out that the best plan is to do a determinant of a matrix. So I said that dr d phi d theta is something times dx dy dz. The something is the absolute value of the determinant of the Jacobian. That's what they use. They use the word Jacobian in this course, right? And that Jacobian has also known as d r phi theta dx y z, also known as that. So basically, not basically, but this notation is reminding us what we need to do is we need to do the partial derivative of each of these with respect to each of these. That's 9 derivatives. And we have to do the determinant of all of that, and it will produce the answer we want. There is a shortcut answer to what this is. I think it's R, but I could be wrong. So I'm just going to have a look it up. I'm going to figure it out, if you don't mind. But before I do that, how are people feeling? Cool. Right. The reason why this is the way it is because a magic trick that determinants do, which is that they tell you the volume of a parallelepiped. based on 3 vectors. So if you have 3 vectors in space and you fill that out to make a neat little, parallelogram-y thing, but 3D, then the volume of if this is like the vectors like A, B, and C, then the volume is the determinant of the matrix, which is made of A, B, and C as its columns, or its rows, doesn't matter, determinant could be either way. Works in 2D as well. The area is made from the determinant of 2D vectors. Determinants were not designed to do this. They just also do this, because maths is like that. Yeah. So there you go. That is just a useful thing to know, and that is one of the reasons why this works the way it does. Because what we're actually doing here is we're calculating a vector. Oh, crap, sorry. I've written this the wrong way around. Yes, this is true, but this is not what we want. Sorry. This is true, but it's not what we want. Sorry about that. What we actually want is this. What we want is this, dx, dy, dz. Sorry about that. And the reason I know we want this is that our expression that we were trying to calculate already had an x, y, z, and we're trying to replace it with something involving drd, r, theta, phi. Okay, we already have this. We need this. So what this means is we're going to have to calculate. We can do it this way, but we don't have formulas arranged in that direction. So we're just going to do it this way. And also we already had this, and what we need is this. So we can do x was r cos phi sine, no, cos theta. Yes. No, sine phi. Ah, sorry. Yep. And so dx on dr is sine phi cos theta, and dx on d phi is the r will still be there because it's multiplied on. The cos theta will still be there because it's multiplied on, and the sine phi will become cos phi. And the dx on d theta, damn it, I don't have room. The r will still be there because it's multiplied on. The sine phi will still be there because it's multiplied on, and cos becomes minus sine. dy, damn it, y is r sine phi sine theta. So dy and dr is the constant. Dy on d phi r and dy on d theta is r sine phi cos theta. And the Z is R cos phi. So dz on dr is cos phi, dz on dr, d phi is r is still there, minus sine phi, and dz on d theta is 0 because there is no theta in z. Okay. And so therefore, my thing that I'm looking for is the determinant of this matrix. Never give myself enough space. I'm going to put some dotted lines in here so I can keep track of where one thing ends and the next begins. And then my y's. And my z's. Right. And the determinant of that matrix, the absolute value of the determinant of that matrix is the thing I want. Cool. Not a fan, honestly. I can see an R down the middle of this column, so I could factorize that out at this time. And I can see an R down this column too, because that's 0R. So I could factorize that out. So I'm going to get R squared. It may have been a waste of time, but here we are. You can do that in any column or any row. If they all have a common factor, you can pull it out of a determinant. I know this because I was helping the Maths 1As with it. Nothing else is really in common, is it? Well, maybe I'll expand along that bottom row because it's the simplest one. It's also got a 0 in it. So let's see. Plus minus plus. So I've got cos phi and the determinant of this matrix. Minus sine phi and the determinant of this matrix. Those plus or minus there they don't make a difference. They're just helping me figure out where this plus minus plus is. Bear with me, I'm just thinking. Fuel. And plus 0, I guess. What I'm doing is probably not the most efficient way. I'm sorry. It's just what's occurring to me on the day. And I can see there's a cos phi in both of those and a sine phi in both of those, so I can pull them out. Oh, look at that. That's cos squared plus sine squared, that determinant there. Ah, pleasant. The sine phi in that column and in that column. Well, and it's the same thing. Look at that. That's cos squared plus sine squared, which is 1. Because it'll be minus sine. Oh, gorgeous. Oh man, it's gorgeous. So that's cos phi squared and a sine phi. And that's sine phi squared and a sine phi. So if I factorize out the sine phi, I'll get cos phi squared plus sine phi squared. Oh, which is also 1. Oh, there you go. Look at that. That's gorgeous. I love it. As far as I know, you're allowed to remember that one if you can, unless you're explicitly asked to prove that this is the correct one. Yeah, and so therefore dx, dy, dz is r squared sine phi. And I just want to check something. This is supposed to be a positive number because we were supposed to take the absolute value. That's okay because phi was between 0 and pi, all the way back here. And sine is positive there. So it's all good. Oh, just a second. dr, d phi, d theta. Now, couple of notes. When you do your integral and actually change the variables, you're going to have to, we know what this is. This whole thing here gets replaced with this. The whole of the dx, dy, dz gets replaced with r squared sine phi dr d phi theta. And then you're still going to have to replace each of these in the formula for f with what they are. So you're going to have to replace your z with r cos phi and your y with r sine phi sine theta and your x with r sine phi cos theta. Let me just check that I've. Yeah, you're going to have to sub all of them into here and also replace all of this with this. So whatever this is, there's going to be an extra r squared sine phi that you're going to have to integrate. And then this is going to be replaced with something with the, the r goes from somewhere to somewhere, and the theta goes from somewhere to somewhere, and the theta goes from somewhere to somewhere. It doesn't really matter what order you put these in. You just have to make sure these are in the reverse order, like when you do it. And once everything's been replaced, then you can do the integral, which is really doing 3 integrals, because that's integration for you. And that works just as well in 2 dimensions. It's just a smaller determinant. It's much easier to calculate. And one of the reasons spherical coordinates is chosen is because it does work out so neatly when you find the Jacobian determinant of the Jacobian matrix. Yeah. Cool. And the reason you might want to do such a thing, to change variables, is it may be much easier to describe the shape of V using your polar coordinates than it is with XYZ coordinates. For example, if V was a sphere, then spherical coordinates is the go. Or if V was part of a sphere. Yeah. Or even if it was a cone, that would probably be fine as well. Like anything that tends to be made of lines through the origin is like a star coming out of the origin. This is probably a good parameterization. So I'm also answering the question of what parameterizations are useful at the same time. Yeah. Now, this is one of the traditional parameterizations, but if you were just given a random one with U's, V's, and W's, you would do exactly the same thing. You would figure out what X, Y, and Z were in terms of U, V, and W, and you would do all the partial derivatives, and you would do the determinant, and then you would replace the dx, dy, dz with whatever it is. Yeah. How are we feeling? Cool. Okay. I'm going to add something here. Oh, yes. Yes, you have to, well, or a description for the volume. It doesn't necessarily need an equation, it just needs to be described. So if they say it is the sphere of radius 1 centered at the origin, then you go, cool, I know how that's described. But sometimes they give you a formula for the surface as well, and you just have to recognize that that is a sphere. While I'm on that topic, just as an aside, while I'm doing parameterization, that is a sphere of radius r. Well, the surface of a sphere of radius r. So this is not the parameterized version, this is the Cartesian version. But that equation, all of the points that satisfy that equation are the surface of a sphere of radius r. Just so you know, in case you're given something like that and you go, what am I supposed to do with this? And you can say, aha. And if you had a less than or equal to r squared, that would be the entire internal volume of a sphere. Okay. And if you're just, while I'm at it, if you have x squared on number, y squared on number, z squared on number equals 1, that is an ellipsoid. It looks like a football-ish. Different radiuses would go with different codes of football. Yeah. So, yeah. But there are lots of other shapes as well. Many shapes whose formulas involve x squareds and y squared, some sort of polar form will be useful, because then the x squared plus y squared becomes a cos squared plus sine squared, and it goes away. Okay. Anyway, a separate point I was going to make, that was an aside. A separate point I was going to make, what is that the whole vibe of actually figuring out an integral in multidimensional space in this course is change of variables. Like, it's everywhere. That's the classic one in the volume integral, and there's a matching one in the there's a matching one in an area integral. But even in a path integral, like a path integral, they call it a path integral, do they? Or anyway, path integral of a scalar function they write it like that, probably. Is that right? The little ds. And what you do is you parameterize the path so that r is, something involving t. And then you go that ds is the length of dr, and dr is like r dash t dt, like that. And so you are already doing a parameterization and doing a change of variables and replacing this ds with something else. It doesn't have to be a t, it could be a theta. Theta is really common if you've got a circle. And so that is also a change of variables as well. And then your path integral of a vector function is like CF r dot dr, probably. Other lecturers use ds in bold, but I think it's dr in this course. And then you go, aha, well, dr is r dash t, which is a vector, times dt. And you replace the dr with this, and you'll have to do the dot product when it comes. So every one of these integrals does the same vibe. You replace your thing with something else by parameterizing it, and your d whatever becomes d something times d something else. What else have we got? Surface integral. Integral of a vector function will be like a double integral across the surface of f of r dot d bold s. I think that's right, the notation. And you'll go, cool, cool. Parameterize so that u and v go to the function, the position r. So r is a formula involving u and v, which is officially x, y, z equals u and v. And then you'll go, cool. This one's a bit more complicated. You have to do dr on du cross dr on dv. And that is what ds is. Yep. And see, that's a vector when you do a cross product. But there's a little du dv, which is a little piece of area that goes with that vector. Whereas a surface integral of a scalar function no dot product this time because it's already a number, so you just multiply them together, and your ds is the length of ds, which is the length of ru cross rv du dv. So they're all changes of variables, always. You're always replacing a d something with something else times a d something else. That makes me feel better about the whole thing. And the most complicated one is the dx dy dz being replaced with something times d u dv dw. Because that's the most things changing all at once at the same time. Yep. That was pretty much for this, which is scalar function across a volume, or scalar function in R2 across an area, which I might as well put in now because I've mentioned it and I haven't written it down. an area region. So that's like you've got something like that called R in R2, and you go the double integral across R of function of x and y dx dy, and you have to parameterize. You can either leave it like that and somehow work out what this is as an integral, invite like you change the x's and then each what x gives you a y that you change, or you can parameterize it and have like uv goes to x, y, and so you can do dx and y on du and v, which is a matrix that has all the derivatives of x with respect to u and v and the determinant of that. And then dx dy is that times du dv. And all of that goes in this spot in the integral here. And in many ways, this is quite similar to this, just here. It's just that the cross product in R2 just gives you a number, not a vector. So, but the cross product is a determinant as well, right? Sort of. Yeah. Okay. So it is useful for me at least, to think about them all as some sort of change of variables. If you're extremely lucky, you will not have to change the variables. There is one situation in which you do not have to change the variables, and that is when the thing you are integrating is a constant. I'm sure there are others, but this is the one that I find easiest to recognize. I do not necessarily, though sometimes I still do, I do not necessarily have to, in fact, change my variables as long as I knew what the volume of V was, because this would be 5 lots of the integral. And now the thing I am adding up across the volume of V is all the little tiny volumes. And so what it produces is the total volume of V. And so if I knew what shape V was, I could get away with doing this integral without actually having to do a parameterization. For example, if V was like a sphere or a cone or a box, I could use the formulas for volumes of things that I learned when I was in year 11 to figure it out. Or I could parameterize it and it would tell me what the formulas are. And it works for areas, and it works for surface areas, and it works for lengths. Like if you're integrating a constant, then you can just involve the length or the area or the volume that's there. Something like that. That is the length of C. And so if C was like a circle, you go, ah, cool, 2 pi r. And if C was a straight line, you would just figure out how long it was. So it's just really important to know that that's a thing. And some people really struggle with the meaning of the number 1 there. What this is saying back here, that's a 1. There's 2 ways of thinking of it. And one works here. It's saying that that 1 is measured in units of area per centimeter cubed. For every centimeter cubed, I accumulate 1 centimeter cubed of, not area, volume, 1 centimeter cubed of volume. It is a rate, it's centimeters cubed per centimeters cubed. And when I add that up across all the centimeters cubed, I get centimeters cubed. The other way to think about it is to know that, I'm going to do one more example. That in the region like this, now this will give me the area of R. If you drew a region on the XY plane and you made one a height, like that, then the volume of this cylinder would be base area times height. So the volume is base area times height, which is the area of R times 1. And so the volume of this region is this volume is the same as the area of the base, because you've made the height 1. It's a little bit like if you want to find the area of something, you can fill it up with little cubes, right? And stack them on the cubes. And technically what you're calculating is volume, but it's area because the cubes are all the same height. So, or you can think of it as accumulating 1 centimeter cubed, 1 centimeter squared of area for every 1 centimeter squared you pass by. That's the other way of thinking of it. How are you feeling? Cool. Okay. Right. Does that give you a good idea of changes of variables? Cool. Anything else to add to that before I move on? Cool. All right. I will sharpen my pencil. So I'm now going to ask if anyone has anything has occurred to them in the intervening time of things they would like me to talk about. Cool, that's on my list already. That's good. Well, sort of.
The region from dx to dy to dy to dx, you have to reevaluate the value of the integral.
It's not a theorem. It's just a thing to do, and I don't think it has a name. It's called reversing the order of integration. You want to talk about that? Okay. No one wants to talk about complex number things? No? Okay. Rightio. I will get on to the Greens and the Stokes and the divergence then. So the the 3 fundamental theorems of calculus, of multivariable calculus, there's another one. Technically there's 4. I don't know what it's called in your course. There's one for curves. I think it's called, when I did the course, it was called the fundamental theorem of calculus for curves. Bear with me, I'm just going to look it up. Nope. I should really show you what's here, shouldn't I? No, I shouldn't, because it's someone else's book and there's copyright issues with that. So I'm not going to do that. You can see it. I'm just not going to put it on the recording. This one. Nope. Yeah, the fundamental theorem of calculus for paths. So there are, in fact, 4 fundamental theorems of calculus in multivariable calculus. Everyone thinks there's only 3 because they've got people's names, Green's and Stokes's and Gauss's divergence, but there's one more. So I would like to talk about all of those. I just wanted to check that it was there. Okay. Okay. I'm just going to draw a picture. This picture is in the 2019 revision seminar. I'll link it here again when I put it on the website. It goes that, like, when you're in one dimension, in 1D, there is only a line, which is the x-axis, and there are only scalar functions. And every point on the x-axis has a number attached to it, which you normally interpret as a height or a depth. And then you do an integral like this. I mean, we do integrals the way we've always did integrals when we first learned them. And in 2D, there are 3 integrals you can do. There is okay, so in 1D, there is just scalar functions along a line. In 2D, there are still scalar functions along a line, but the line doesn't necessarily have to be straight, right? Scalar function along a path, and that path could be anything. And there's also a vector function along a path. And so this one, there's a number at every point. And in this one, there's a vector at every point. And there's also a scalar across an area. And these are the 3 different integrals in 2D. Theoretically, you can do other ones, but these are the ones that are in the theorems. And then in 3D, there's 5. So you can do scalar along a path. You can do a vector along a path. You can do a scalar across a surface. And so back in 2D, all areas were flat, but now surfaces can be curved in 3D. And you can do a vector function across a surface now. And then in 3D, you can do a scalar function across a volume. I believe technically you can do a vector function across a volume, but nobody knows what it means. And you would think that there's probably something here, some sort of tensor along a path, theoretically, is a thing that you could do. But that's not in your course. But I don't know. You never know what physicists will come up with. So these are all of the types of integrals that are involved. And the ordinary fundamental theorem of calculus lives here, right? And the ordinary fundamental theorem of calculus says that the integral of a function from one place to another along the line is capital F of B minus capital F of A, as long as f dashed of x is little f of x. So you've got to think of something that differentiates to produce this answer, and then you can do it. And that is the ordinary fundamental theorem of, well, part 2 of the ordinary fundamental theorem of calculus. And in 2D, there's a theorem here that just goes with paths, the scalar functions along a path, and it says that the integral along a path of a scalar function ds is f of like b minus f of a, as long as little f is the gradient of big F. When little f of r is the gradient of big F of r. And A and B are the ends of the curve C. And C goes from A to B. And this works perfectly well also in 3D. So I'm just going to write that down again on a separate piece of paper, but I just wanted to show you where it was. And then in 2D, there's another fundamental theorem of calculus which connects these two things together, which is Green's theorem. And in 3D, there's one that goes there, that's Stokes's theorem. And there's one that goes there, which is Gauss's divergence theorem. I'm going to write them on a separate piece of paper so it's not all bunched up here, but that's where they live. Gauss's divergence theorem connects a vector integral across a surface with a scalar integral across a volume. And the surface happens to be the boundary of the volume. And Stokes's theorem connects a vector integral across a surface with a vector integral along a path, and that path happens to be the boundary of the surface. But they all work only if the function that goes with the bigger integral is a derivative of the function that goes with the smaller integral. That is how it goes. So here, this only works if this function, which goes with the integral, is the derivative of the function that isn't in an integral. Okay, here we go. So just going to say the traditional fundamental theorem of calculus in 1D is that the integral from a to b of f of x dx is f of b minus f of a when f dashed of x is little f of x. And this is traditionally written as, you know, the thing with the square brackets, you know, f of x, a and b, like that is short for this. We're just sort of imagining that there. That is the fundamental theorem of calculus in 1 dimension. And I thought I would put it there because, you know, we might as well start there. Then there is the fundamental theorem of calculus for paths, also known as the fundamental theorem of calculus for curves. Curves and paths are the same thing. And the fundamental theorem of calculus for paths can be written in 2 ways. This is how I prefer to write it. The integral along a path of f of r ds. So that's a scalar function, is capital F of b minus capital F of a when little f of r is the gradient of big F of r. Yep. So big F, this is a scalar function. Oh crap, no, this is a vector function. Damn me. I was wrong. It's not this. Sorry about that. This is a dot dr. Sorry, everybody. I can always adjust this when I actually write it down. So it's actually a vector one. Oh, I feel so much better about that. I was a little bit worried about, yep, weirdness going on. It's okay. It's a vector function. And the reason I know it is because the gradient of this has to be a scalar function or I couldn't subtract it. And the gradient of a scalar function is a vector. So there you go. That's better. Sorry about that. I want to convince you that it's supposed to be a vector in another way. It matters which direction this f of x is pointing relative to the dx. Because if you trace this curve backwards, from b to a, then you're supposed to get a minus answer. So it matters which way the dx is going relative to the way the function's going, but which way the path is going. So, anyway. So, fundamental theorem of calculus for paths, and I'm just going to do one more check just to see if I've got it right. Yep, I was right. Is that if you do the vector, an integral of a vector along a curve, then it is some other function, the difference between a scalar function, when this is this, and C goes from A to B. Yep. So some people prefer to write it like this, that the across C of delta f of r dot dr is f of B minus f of A, as long as C goes from A to B. But for some reason, this works for me better. And this works both in 2D and in 3D, and presumably in 4D and 5D and however many dimensions you want. Does anyone have a question about this? Or a comment? It's it. Same as ordinary integrals. I will point out something important at this time. A vector field which happens to be the gradient of a scalar field is called conservative. Usually it's minus the gradient of a scalar field, but whatevs. So note, if f of r is equal to gradient of f of r for some capital F, then little f is conservative. Yep.
In terms of the two-dimensional integral over the surface?
No, there is no surface.
But how do we know B and A?
You have to just know that your curve has a beginning and an end. And it's a curve. So it's not a surface, it's a curve that goes from like A here to B there. I think we need an example to really make sense of that. Maybe. We were in 2D there, but the curve is one-dimensional, yes, but it's in 2D space or 3D space or whatever dimensions you need. Because you can do gradients everywhere. You can only do curls and divergences in 3D. I mean, officially, I'm pretty sure you can do them in 7 dimensions as well. But This is just what David Roberts tells me, so I'm just not going to go there. Yeah, so it's worth noting that this is the first fundamental theorem of calculus for multidimensional space that you were told. It's just not in the section that's called calculus theorem, fundamental theorems of calculus. It's in the section before that. Sneaky. So, or just forgetful. Oh, I already had a page 9. That's bad of me. Okay. So you'll see in my diagram here that these just go sort of off into space on the side of my diagram. They kind of go to 0-dimensional integrals because that's what just subtraction is. Because what you're interested in is only what is happening at specific points, which are 0-dimensional objects. So, okay. So Green's theorem, I have a very idiosyncratic way of remembering it. So I will write down my version and then I'll get eventually to the lecturer's version. So Green's theorem connects a scalar function being integrated across an area in 2D. So it's an only in 2D. It's like worth noting that. It integrates scalar across area and a vector bear with me, along a path. These are the two things that Green's theorem connects. So you have a scalar function like that, and a vector function. Oh, that's got to have a different name, doesn't it? This is not how it's written in your course. But this is how I think about it. When, and this is a closed up integral because this curve meets itself, comes back to its starting point. It doesn't really need to be there, but it just reminds you that the curve C comes back to its starting point. When little f is a specific derivative of this function. It's going to take me a little while. Here we go. When f of xy is p, just a second. I want to see what your lecturer calls it. It's probably called U and V, isn't it? Yep. Is U of xy, comma, V of xy. They are the two coordinates of this vector function. It produces two coordinates. And f of xy is, now bear with me. They're both here. I'm pretty sure it is dv on dx minus du on dy, but I will just check that. It is. And I remember that because the x and y are in the correct order. And each of them goes with the other coordinate. So that is an extremely specific derivative. It's of this function f. It's not the gradient of f. It's kind of like what is that? It's the curl of f actually, but it's an extremely specific integral, and C is the boundary of R. Yep.
It's normal F in three-dimensional ratio that mentions.
Yeah. So if you pretend you're in 3D space and your R is a surface that happens to live entirely in the XY axis plane, and everything has a third coordinate, which is 0, this will work out as Stokes's theorem. But that's not how it's written. And I'm just going to write it the way that your lecturer writes it. If you've ever seen me do integration by parts, you'll see that I do not write it on the page in the order that it is read aloud. I'll write this bit over here, and this bit over here, and this bit over here, and this bit, and construct it. And that's how I think about Green's theorem. I've got these two integrals are related, but only if this is a derivative of that one, and it's this specific derivative. So, yeah. So in your notes, it's written like this. No, not there. And that's not a U, it's just a V that looks like a U. I'm writing it down from the notes, but you can see what the notes say. All right. I'm just going to put that in its own line. Okay. So when I am doing this, so this here is what's in the notes. But note that u dx plus v dy is the dot product of u v dot dx dy. Because you'll get u times dx plus v times dy. And this is dr. Yeah. So Green's theorem is easier for me to remember in this format than this format. Yeah. And this little symbol here stands for the boundary of R. Our curly D, backwards curly D there is doing a lot of work here, because here it means the partial derivative and here it means the boundary. So to be fair, if the region R grew just a tiny bit, then the space on which it grew would be the boundary. And so it would be dr. Bit dodgy, but anyway, there you go. That's Green's theorem. And Green's theorem is, well, it's Green's theorem. It's fine, I guess. Really nice for finding areas of things. Have you seen a planimeter? Did your lecturer mention planimeter? Well, they should have, and I'm glad they did. A planimeter is a device for measuring area by tracing around the boundary of a shape. This is something that is worth sharing on the there you go. It's a planimeter. And it's got a little device here that counts out the area as you trace around the edge of a curve. And it uses Green's theorem to do its job. Pretty cool. I've never seen one in real life. I should probably one day buy one for the Maths Learning Center, because that'd be cool. Or make one. I have an intense desire to make a human planimeter where, anyway, people holding hands could do the job, but maybe that's something that I don't know if it even is a possibility, but wouldn't it be cool? Yeah. I'm going to repeat that. Is the whole point of the theorems to make it easier to solve the integrals? I think yes, but also no. There's just these are how these things are related. But it is sometimes easier to. It's usually easier to integrate a scalar function across a region than it is to integrate a vector function around a curve, or vice versa. Sometimes the other one's easier. Because for this one, you have to parameterize the entire inside of the region, or have the whole, limits with x and then the limits with y involve the x's, and that can be really complicated. Whereas if the boundary is easily described as like a circle or something, then that can be quite straightforward to do that integral, because it's all in terms of one variable. Yeah. But sometimes it turns out that when you do the derivative of a thing, it comes out to a constant, in which case this is just the area of the thing. And so I think that it's used in both directions to make integrals easier, but you never know exactly which direction is going to be the one that makes it easier today without looking at your actual functions that are involved. Yeah. So this path integral of a vector function and also the area integral of a scalar function, and how those two things are related to each other. Yeah. All right. I believe it gets, so anyway, I don't know all the history of it, I'm sorry. Stokes's theorem. Actually, going to start with the divergence theorem. Am I? No, I'll do Stokes. Stokes's theorem also connects an area. It connects the same things in 3D as Green's theorem connects in 2D. It's just that it's a surface, not a area, because it doesn't just work on flat things. So Stokes's theorem works on surfaces and paths. So you have surface of a scalar function. I'm almost certain. Just let me look it up. Pretty sure, but bear with me. Should be in a box, right? No, it's a vector. Of course it is. That would be too easy. Oh no, I wrote it in the correct spot on my diagram before. So Stokes's theorem is here. It connects a vector across along a path with a vector across a surface. And the reason why back in 2D, Green's theorem didn't do that is because, well, I don't know. Because Stokes's theorem, the vector has to be perpendicular to the surface in order to work. So back here, the only vectors perpendicular to the surface are not in 2D. And so they don't count. So they're just numbers. Yes, I knew that there was a reason. Okay, but the surface integral of a vector function and the path integral of a vector. That's what Stokes's theorem talks about. But the two vector functions involved are different vector functions. And so Stokes's theorem connects a double integral across the surface of a function dot ds, like that. So this is a vector function. And a path integral also of a vector function. And this path is also closed up. So this is true when this function is a derivative of this function. And the correct derivative is the curl. And that's how the fundamental theorem of calculus works. It says that the two integrals will be related will be equal as long as the thing that has more integrals with it is a derivative of the thing with less integrals with it. This is a thing with one integral, and we have to have a derivative with two integrals so that the derivative in some sense cancels out one of the integral signs. So, and it's the curl today that is the correct thing. We've already had one with the gradient. That was the fundamental theorem of calculus for paths. Now we have the curl, and the other one has the divergence. And I would not be surprised in the least if the invention of the curl and the gradient and the divergence exist specifically because it makes these integrals work. I would not be surprised. Much of what happens in the reasons why things are done in physics maths are circular. The maths is chosen so that the physics works the way it should. So I would not be surprised. And one of the reasons I think that makes curl so difficult to understand is partly because it was invented to make the integral work. So anyway, that's a theory of mine anyway. I'm sure that some other people who know some more of the history will be able to correct me on that, but it makes me feel better, so I'm going to run with it. So when this is that, and C is the boundary of S, by the way, a surface integral of a vector is called a flux, because physics. It just doesn't roll off the tongue quite so nicely in Back to the Future if he talks it as the surface integral of a vector capacitor. Thank you. It was really bad, so I appreciate the pity chuckle. So anyway, C is the boundary of S. And just important that S can be looking like anything at all, and it doesn't like close up to itself, the surface. It's got an edge. And you know that a surface has an edge if when you are nearby to it and you keep going in that direction, you fall off the surface. So this is C and that's S there. Okay. So that's it. So this is basically saying, while it is technically possible to calculate this directly, if this function is already the curl of something else, then you can calculate it this way instead. Yep.
So dr points towards the so
This dr here. No, dr points along. ds always points outwards from where you are, perpendicular to the surface, and dr points along that. Dr points along the boundary. Yeah. Cool. Nice. And the idea is that the vector parts of the vectors that are perpendicular to the surface, which is what this bit's doing, when you add them all up, you get the same answer as the parts of the vectors that are in the same direction as the boundary, but only if this vector is already the curl of that. So it's worth pointing out that the thing that this vector is being dotted with is a completely different thing from what this vector is being dotted with. This one's being dotted with capital F, and this one's being dotted with little f. And the short version of that is the double integral across the surface of the curl of f dot ds is like that. That's the short version. Okay.
Yes.
Oh, yeah, it's a bit dodgy. DS is a vector which represents the direction and the area of a small piece of the surface.
But it happens to be the
Yes, that is crazy.
but it happens to be S as well, right?
Sorry,
that happens to be C.
This is C, yeah. So as long as this is the boundary of that, and this is the curl of that, it'll work. Yeah, this DS is like the RU cross RV du dv. Or the N hat du dv, depending on the flavor of the mum. Yeah. Yep.
What is the function F? Scalar function F and the vector function.
This is a vector function, and that's a vector function too.
Right. On graph, what are they situated?
Everywhere. So like there is like the idea is that at every point on the surface, and in fact everywhere in space, there is a little function F, which is a vector. Everywhere. So I've got
that surface. Yeah.
And everywhere in space, nearby to the surface. But also in particular on the surface itself, every point you can calculate a vector that goes with that point. And then this function at every point on this curve and also everywhere, there is a vector that goes with the point.
But the vector value function, geometrically, would it have a different sort of representation to what compared to the scalar value function?
Yes, it would be a vector and not a number. Like when people think about vector functions, they think about there being a little vector everywhere. Every point has a vector at it.
What is scalar function we're talking about points of the curve?
And with a scalar function, there is a number everywhere. Every point has a number of its own. So you know back here when I drew this, every point everywhere has a number of its own for this function here. And the difference between that and this is that with this, every point everywhere has a vector of its own. And that vector may be the force that is being felt at that point, possibly. Could be the force of gravity or electromagnetic force or what. Or it could, for example, be the speed at which the particles are flowing fast at this point, like the velocity, because it's the vector of which the particles are flowing past at this point. Or it could be the curl of that velocity field. Yes, which is a whole other thing, which points in the direction that the perpendicular to the general direction that things seem to be swirling in. Something like that, some sort of magical physics thing. I've never understood what the curl is, I'm sorry. I do know that if a vector field is flat like this, and at every level it's flat and goes around this way, then the curl will point upwards. I do know that that is the truth. Like the right-hand rule. If the vectors tend to go round that way, then the curl will go up, and vice versa. So that is that. And so what this means is that if you have a vector field, you've got a formula for what this is, then you can calculate, if you want, this thing without directly parameterizing this curve, as long as you have a parameterization for the surface. But it's much easier to go this way. If you have a function that happens to be the curl of something else, which is, what that means is your function is, just a second, there's a word for it. Solenoidal. A solenoidal function is already the curl of something because its divergence is 0. That's right, isn't it? Or is it the other way? No, that's irrotational, is curl is 0. Yeah. So if you've got a function that's solenoidal, then it must be the curl of something. And if you can find the thing that's the curl of, then you can, instead of parameterizing the entire surface, you only need to parameterize this curve and do this integral instead. And that's why it's easier, especially in 3D. The Green's theorem is like, yeah, whatevs. But Stokes' theorem is like, yeah, it's really hard to parameterize some surfaces, but curves are not as hard to parameterize usually, especially if they're circles. Okay, cool. And it's really important that you know that that it's possible to calculate these functions everywhere that contains the whole surface, because you need it to be able to pass its values nearby to the other ones. Like it needs to change slowly across that, not slowly, but predictably, across the whole space that's here. Okay, that's Stokes' theorem. And the last one is Gauss's divergence theorem, sometimes just called the divergence theorem. But, you know, if we're going to give the other ones names, we should give this one names too. What's that? What? No, neither of them represent the volume under the surface. No, they do not represent the area either. They represent whatever this function is and how much it's pushing on the surface, or how much it makes the surface move, or something else entirely. It could be any number of things, but this is never the volume, this is never the surface area of the surface, this thing, because the surface area of the surface is a scalar function integrated across the surface. And this is not the length of that curve either. So neither of these is a length or an area. They are a pressure or a move or a total movement or a mass or whatever. Like they're all, yeah. I'm sorry. That's one of the big things to stop making you think is like that the answers to these are areas and volumes. Then what if the units are that the things are measured in? And they're most often being like movement. Like they're a number which is like a total amount of change usually. Yeah. Flux being the amount that something changes across the surface as it moves through the surface itself. Right, says Cronk. Gauss's divergence theorem. According to my original diagram there, and I'm just going to try and remember it without looking at it, Gauss's divergence theorem connects the integral of a vector across a surface with the integral of a scalar across a volume. Yeah. No, not there. There. That was in 2D. There. So there will be an integral across a volume of a function dv. That function's like x, y, z, right? I'm going to call r. It is a scalar, yes. But the one that's on the other side is a vector. Because the divergence is a scalar. And this is also closed up. All right, so we're going to need this to be a derivative of this, and the correct derivative is the divergence. And the S is the boundary of the volume. So there's some sort of volume, and like the volume's on the inside and the surface on the outside is what S is. That is Gauss's divergence theorem. And the short version is to just put this in that spot there. Right. So the short version is and this is the boundary of V. So in this case, this has to be the divergence of that, and this has to be the boundary of that. And then it'll work. And this we've already talked about. This is a flux here as well. And it's worth noting that a function that is the divergence of something is irrotational. Because the curl of a divergence is 0. Yay! So there's a name that goes with each of the kinds of functions that appear in these theorems. The fundamental theorem of calculus for paths concerns conservative vector fields. The fundamental theorem, the Stokes' theorem concerns solenoidal vector fields, and this concerns irrotational things, scalar fields. Possibly, I may have my words wrong. It's okay. We'll get there. No, irrotational are vector fields. Sorry about that. I really thought that was neat, but it's not neat. Damn it. Yes, but you cannot get away with at least one of these integrals will have to be done by doing a parameterization, unless you're extremely lucky and this comes out to a constant, as we said earlier. But no integral can be calculated without a parameterization unless you just happen to know the answer already because it's an area or a volume or something. Yep. If this comes out to a constant, oh, well, when I say constant, I mean it is definitely a number, but it's a different number for every position R. But if it's the same number, no matter what R is, then you can bring it out and you'll have a volume here. So when I say constant, I mean number that is always the same. Okay, so they are the three theorems, and they are related to each other in those ways. There is a classic question that is in one of the tutes or something that is worth mentioning. Gauss's divergence theorem talks about a vector function being integrated across a surface, and Stokes' theorem also talks about a vector function integrated across a surface, but it is worth noting that this surface is the boundary of a volume in 3D. In Gauss's divergence theorem, this surface has to be closed up, has to be closed. Whereas in Stokes's theorem, this surface does not have to be closed because it has a boundary. It can be, and if it is closed, then the answer is 0. Because the path is just a dot. So Stokes's theorem, and also it's worth noting that Gauss's divergence theorem requires this to be the derivative of whatever this is, and Stokes's theorem requires the function here to be a derivative of this. And so if you're going to connect them up that way, then this function has to be the divergence of a curl, which is always 0. And so it doesn't help to connect them together, because for this to work, this has to be the divergence of this function. And for this to work, this has to be the curl of this function. And the only way that can happen is if this is the 0 function. And so they don't link up. And I mean, it would link up even further this way. Like you could have the divergence of the curl of a gradient, and that's just going to be 0 in all directions. So yeah, sadly, you can't connect them any further than you can, than the two, because the function has to be really, really special to connect all the way to the end. Yeah, which is a really hard question to answer in an assignment, to say the words right. But yeah. Yeah, there was an assignment question or a cheat question or something that says, why aren't all scalar functions across volumes equal to 0 if Gauss's divergence theorem and Stokes's theorem are both true? And the answer is that Stokes's that this surface has to be closed, which causes that its boundary is just a dot. And so when you integrate from one place to another, when there's no places to be, you just get 0. They are the theorems. But what they require is you to be able to do at least one of the integrals the long way by parameterizing the function itself. Yeah. And there is a classic way of writing assignment/exam questions where they'll give you two integrals separately, and they won't make it obvious that these two things are derivatives of each other. They'll just have a formula here and a formula here. But in part A, you will have calculated the divergence of, or the curl of this function, and you'll go, oh, look, it's like minus this or something. So you can notice based on your previous working that one of them is the curl or the divergence or the gradient of the other. So just keep it in mind. And that's why I like holding this version in my head, is that I can connect two integrals as long as I can show that this, for Stokes' theorem, as long as I can show that this is the curl of this. Yeah. All right. Any other questions? This is the biggest bit of the course, right? The integrals bit. A lot of stuff to do, a lot of pages of writing. It's my favorite bit because it's the bit that's connected to itself the best. Yeah. Plus, I used Plato when I did the revision seminar in 2019. That's always a win. The trapezium I drew on the floor in 2019 so that I could see where the room camera the part of the floor it could see is still there. Partly because the glue on that tape is pretty strong, and partly because no one in a classroom removes anything and for fear that it's important. So it's still there. And it is the part of the floor that the camera can see. Yeah. Okay. Well, I think that'll do. Yeah. Cool. See ya.